Have you ever really stopped to think about the absolute magic that's happening inside your refrigerator? It's this quiet hero in our kitchens, but it's a technology that literally shapes the world we live in. So today we're going to break down exactly how it works. We're talking about the refrigeration cycle.
It's kind of weird when you think about it, right? It seems like a total paradox. Your fridge plugs into the wall, it uses electricity, it even gets warm on the back, and somehow the inside gets freezing cold. So how on earth does a warm box use energy to make things cold? That is the question we are tackling today.
Okay, so here's the big secret, the whole core idea. Refrigeration is not about creating coldness out of nothing. You can't really create cold. Cold is just, the absence of heat. So what your fridge is actually doing is a brilliant little physics trick. It's a heat-moving machine. It's designed to grab the heat from inside the box and just dump it somewhere else, in this case, right into your kitchen.
So to pull off this heat-moving mission, we need a special agent, a hero, if you will. And that is the star of our show, the refrigerant. Think of it as this special fluid whose whole job, its entire mission, is to grab that unwanted heat and haul it away.
All right, so what makes this stuff so special? Well, its superpower is that it can change from a liquid to a gas and then back again super easily. And here's the trick. Every single time it changes state, it either sucks up a huge amount of heat from everything around it or it releases a huge amount of heat. And that ability, that's the key to this whole thing.
Okay, so our hero, the refrigerant, is on this constant, never-ending journey. It's a 4-step cycle, and we're going to follow it step by step to see exactly how it snatches the heat from inside the fridge and just kicks it out into your kitchen. All right, let's dive in. Our journey starts inside the fridge itself. This is step 1, evaporation. And this is where the actual cooling happens. This is where our hero goes in to capture the heat.
Now, I know this chart looks a little intense, but don't worry. It's basically just a treasure map for our refrigerant. The up and down axis is pressure, and the side-to-side axis is how much heat energy it's carrying. So we start down here at point B. Right now, our refrigerant is a really cold, low-pressure liquid. As it flows through these coils inside your fridge, it starts soaking up heat from your leftovers, from your milk, from everything. And as it does that, you can see it travel from B to C. It's literally boiling and turning into a gas. Boom! Heat captured.
And this formula you're seeing, that's just the scorecard for this step. We call it the refrigerating effect. You don't have to worry about the symbols, really. All it's doing is calculating how much heat our hero just absorbed. It just measures the change in energy from point B to point C. It's the official score of how much cooling we just accomplished. Okay, so our refrigerant is a gas now, and it's carrying all that heat it just collected. But now we need to get it ready to dump that heat. That brings us to step 2, compression. This is where we pump some energy into the system to set up the next big move. Let's look at our map again. The refrigerant gas is now going from point C all the way up to point D. And look at that jump. Both its pressure and its temperature just shoot way, way up. That's the compressor doing its thing. It's really the heart of the whole system. It's just squeezing that gas, making it incredibly hot and putting it under a ton of pressure. Much, much hotter than the air in your kitchen. And that is what you're paying for on your electricity bill. This formula, the compressor power, it's just measuring how much work that compressor has to do. It's the energy we have to put in to take that low-energy gas and turn it into the supercharged, high-energy state we need for the next step. This is the cost of getting that cooling. So now our refrigerant is a super hot, high-pressure gas, and it's just loaded with all that heat it picked up inside. It's finally ready to get rid of it. Welcome to step 3, condensation. And this is all happening on the outside of your fridge.
Back to the map, we're on the move from D back down to A. And if you've ever felt those warm coils on the back of your refrigerator, this is what's happening. Because a refrigerant is now so much hotter than your kitchen, that heat just naturally flows out of the coils and into the room. And as it loses all that energy, it cools down and condenses back into a liquid. And just like that, mission accomplished. The heat has officially been moved out.
And this formula here for condenser capacity, this just tells us how much heat we successfully kicked out. It's calculating the total amount of heat ejected into your kitchen, and that includes both the heat we took from your food and the heat we added when the compressor did its work.
Okay, so our refrigerant has now ditched its heat, but it's still a high-pressure liquid. It's not cold enough to go back inside and absorb more heat. So we need one last, super important step to reset the whole cycle. And that is step 4, expansion.
Look at our map one last time. This is the final leg, the journey, this dramatic vertical drop from A straight down to B. What's happening is that high-pressure liquid is being forced through a tiny little nozzle. It's kind of like when you spray an aerosol can and the can gets really cold. This sudden release of pressure causes a massive plunge in both pressure and temperature. And now, our refrigerant is intensely cold again, and it's ready to go back inside the fridge and absorb a whole new batch of heat. The cycle is now complete and ready to start all over again.
So this cycle just goes on and on and on. But how do we know if it's actually doing a good job? I mean, how do we measure how efficient it is?
Well, for that, we have something called the coefficient of performance, or COP for short. The best way to think about it is like a bang-for-your-buck score. It just tells us how much cooling we got for the amount of work we had to put in. And just like with any score, the higher the COP, the better.
And when you look at the formula, it's actually really simple. The COP is just the refrigerating effect. That's the cooling we wanted, our goal, divided by the compressor work. That's the energy we had to pay for, the cost. It is literally just a ratio of what you got versus what you spent. And the higher that number, the more efficient your fridge or your AC unit is.
Now, what's so cool about this is that this elegant little four-step dance isn't just happening in your kitchen. Once you understand the basic idea, you start to see this cycle absolutely everywhere.
Think about it. That exact same process, evaporation, compression, condensation, expansion, that's what's powering the air conditioning in your house and in your car. It's what keeps entire aisles of food fresh at the supermarket. It makes huge industrial cold storage facilities possible. I mean, it is truly one of the fundamental technologies of our modern world.
So there you have it, this incredible cycle, constantly working to move heat, keeping our food safe and our homes cool. The really big question, though, for engineers and, for all of us, is this. Now that we know how it works, how can we make this essential process even better? How can we make it do the exact same job, but with even less energy? Now that is the challenge for the future. Thanks so much for tuning in.